Hello everyone. Hope this video finds you well. Today we're going to go into a huge block of reactions, mainly Williamson ether synthesis, bromination, and chlorination. So I hope you guys are all studying up as well. So let's jump into it now. Alrighty, cool. So ethers, we talked about that in the previous video titled ether and ether reactions and oxymercuration, demercuration. And today we're going to talk about just ways that you can make ethers, right? So basically, this is just making ethers. Now, the first way that we're going to talk about making ethers, right, is making symmetrical ethers. So this is going to make symmetrical ethers, this reaction right here, right? And so just for reference, right, this is a symmetrical ether, right? One, two, three, one, two, three. Yep. And so ethers that obviously, draw line symmetry down them, you can kind of tell that they're the same on each side. And so we're going to quickly just move this out of the, oh, excuse me, move that out of the way. And the reactants, right, are you have your ether, right? You don't have to add anything else to it, right? Assuming that you have a bunch of ethers that are just kind of floating in solution with each other, right? This will work, right? And then you have H2SO4, sulfuric acid. Then you have heat. This triangle indicates heat. And so, generally, right, you're going to end up with this, right? And so let's kind of go over the mechanism to get there. So it's basically like, this is pretty simple, I would say. It's just a huge, just a large stream of proton transfers. So let me go ahead and quickly kind of draw out sulfuric acid here. I just want to make sure I'm doing this correctly. Hold on, let me check my notes. The structure of sulfuric acid always escapes me for some reason. Okay, cool. Yeah, that should be correct. Alrighty. So the first step here, right, is that you are going to do a proton transfer, right? Since sulfuric acid, right, is an acid, it's going to give off its H. You're going to end up with this right here. Don't forget that plus charge. If you get your plus charges, you're going to see your points tank, and it's going to be like death by 1,000 cuts. So that's never going to be fun. Turn that red. I'm going to turn this red. Okay, cool. So hopefully this makes sense, right? So you stole an H from the sulfuric acid itself. Then from here, right now you now have a uh, you now have a OH that has an extra H on it, and therefore it has a plus charge. And then from there, right, you are going to then take another one of your starting materials, right? This is excess. Remember, excess. Or same structure that you have in excess. So this is basically just another one of these, right? Then from here, you are going to conduct an SN2 reaction. This is going to pop off. And then you're going to end up with we can go ahead and kind of move and color code this for you. If you're confused, feel free to pause. Right, I'm going to quickly highlight this to make sure that you understand. Right. Right there, right? And then you have this kind of, oh, on its own here. What's that? Yep, good times. And then from here, right, to get all the way up to here, all you do, right, is that you do a quick deprotonation. It doesn't really matter what you use in this case. I can just honestly just use this, right? Deprotonation. And then you end up with this. Yep. So just to recap, right? So you take your alcohol, right, initially, and the alcohol will then grab an H from sulfuric acid. And then from there, right, you'll take another equivalent of your starting material, right? Your alcohol. Alcohol will move to react. This will pop off, and then you'll end up with this right here, right? You'll have an ether, right, that has a H attached to it, right? It's giving it a plus charge, and then from there you do a quick another proton transfer, and you end up with your end material up here. So that's for symmetrical ethers, right? Now, what about asymmetrical ethers? So asymmetrical ethers, right? Relatively simple as well. All you really need to do, right, is have sodium hydroxide, or no, sorry, sodium hydride. I apologize, sodium hydride, NaH. And so the mechanism for this will be pretty simple and whatnot. Like the Na plus and the H will break up. You'll have H minus and Na plus. If you remember, right, this is a hydride. Yep. And so all you gotta know is that sometimes you could have H's that are in in certain molecules that are essentially nucleophilic, right? And so this is one of them, right? So the sodium hydride. So the sodium hydride, right, will go, right? It'll move very, very nucleophilic. It'll move to attack this, right? Move to attack this, and then this will hold on. This will pop off here. Oh, sorry, I apologize. Whoop, wrong attack site right here. This will pop off right here. There you go. Oopsies. And then from there, right, you will create this right here. And so from this step, right, your H2 will bubble away, right? Because this will form H2, right? Because the joining of these two H's right here will form H2, right? Go ahead and I'll highlight this in red. Highlight that in red. Highlight that in red for you to see. Yep. And then at this point, right, you can literally just add on this. You've now created this oxygen over here is now nucleophilic. You can add on literally whatever ether you want. You can literally just add, I can add like something like this, right? I'll throw this in. This is the next step coming into here. Sorry, I'm wasting the color, right? So the next step is you just kind of take this and, right? Next step, you take this in, and then from there, right, whatever ether you want, this will, oops, this probably should be a leaving group. This will come into here, attack, this will pop off. And then from there, right, you will get your asymmetric ether. Yep. Or unsymmetrical ether. Unsymmetrical? Asymmetrical? That's what that's what Dr. Ko has in his notes. Asymmetrical ether. Asymmetrical. One of these two. But you basically get the point that they're not equal on both sides, right? This has three carbons. This has two carbons on this side. I personally prefer asymmetrical. It's one of my favorite words. So yeah. So that's basically all the ether stuff. From here, we'll go on to the next reaction, bromination. Now, bromination, right? The predicted product of this, the PTP for this, that you basically just replace an OH with Br. It's relatively simple, I would say. And so here is the mechanism for that bad boy. I'm pulling up my notes right here. Okay, right. So, and then from here, you're going to also form, oh, the byproduct of H3PO3 phosphonic acid. Not really that relevant, I would say. I mean, but it's good to know, I guess. So the reaction mechanism here, right, starts off with the first step, and that's going to be attacking the PBr3. The reason why, right, we're attacking the PBr3 is because there's so much, like Br is really, really electronegative, right? So it's like sucking all those electrons out of P, right? Making it super, super electropositive. And when that happens, right, it's going to facilitate this reaction. One of these BR is going to pop off. And I'm going to highlight this, right? This is a different BR right here. This is a different BR. And then from there, right, you are going to go on to the next step, right? You'll have an H right here. Right? Plus charge right here. Yeah. So as you can see here, right? This kind of moves in, lassos the PR, right? This is its own compound that I translated over to here. Then this Br over here is going to piss off and do its own thing. And then from here, right, the second thing that's going to happen is that that Br is going to do a quick proton transfer. We're gonna end up with this bad boy right here. Mm-hmm. Ends up with this acid right here, whose name I probably forgot the name of. But then the next step is that this phosphorus over here is going to go into here, attack, and grab, sorry, not attack, but do a proton transfer and grab that. And then promptly from there, we'll go on to here. Is it a little complicated? Yeah. It doesn't make the most intuitive sense, but just kind of have to figure out the motions. And from there, this bromine is going to come into here, do a quick SN2. This is going to pop off on its own. Oops. And then from there, you end up with this BR right here. Yep. And so yes, that is bromination right there. Now, the unique thing about PBr3, right, is that you can do this reaction three different times, right, with three equivalents, right? Because if you notice right here, right, PBr3, right? We only use one BR for one reaction, right? So you can literally do the reaction three different times. You can do reaction next times. You know, if you love chemistry so much, you want to do it two more times. But yeah. And then from there, right, this thing right here, right, will become your after you finish reacting with three equivalents, right, you're going to end up with this phosphonic acid right here. H3PO3. All this stuff is really just extra stuff. I want you guys to kind of memorize the main reaction right here, right? Where first and foremost, right, in bromination, right, the goal is to replace an OH with a Br, right? So just slapping a Br onto whatever alcohol that you had initially. And then from there, right, that O is going to go in, attack the phosphorus, right? It's going to kick a Br off. And then from there, right, that Br is going to swing back in, right, and do a quick proton transfer, right, and eliminate the H that was there originally. Now that H is then going to go, and that P is going to go onto that phosphorus via proton transfer. And then from there, that BR is going to quickly sneak the hell back in, pop, that's going to pop off, that's going to become BR right here. Yep. It's the main point of bromination right here. Okay, cool. Alrighty, so the next one is chlorination. I want to say this one's a little bit more complex, but not by that much, I would say. So the goal, right, is to have this start off with an OH. You introduce I call it Sockle 2 because it just makes sense to me. And the goal is to put a chlorine onto this. Yeah. Chlorine. And so the unique thing about chlorination is that I would say it's pretty you can do SN2, right, without changing the stereochemistry, right? The stereochemistry remains intact. So this is the very unique thing about chlorination. Retains stereochemistry. Yep. And so the reaction goes like so. So you have SOCl2 here, right? Cl2, oops, Cl. First step is that it comes onto this S, right, and it kicks up this bond right here. This is a very, very common motif in a lot of reactions, right, where you have an alcohol, it'll react something that's double bonded to oxygen, and the double bond will be removed and pushed up like so. Here's your plus charge right here. Okay. And then from here, right? So this is a very unique step, right? Where you have this original O right here, right? We're going to highlight that in different colors so you to see here, right? Oxygen over here is now going to slam back down like a superhero in a movie and kick something off. Imagine like a, Captain America falling out of the sky and like, landing, like a superhero, boom, pops off like that. All right. And then from here, make sure to draw very carefully so you don't miss anything. We're going to end up with the S kind of, the sulfur is going to stay there. End up with this again. You have Cl chilling over here on its own. Now the Cl, right, that we just kicked off, we'll highlight this right here, right? Highlight this yellow. God, I hope none of you are colorblind. I'm so sorry if you are. I apologize if it's kind of hard to see, right? The Cl that's now kind of yellow, right? Will then go and can I change this to yellow? Thank you. We'll then do a quick proton transfer all the way to here. That'll pop off onto there. Right. Then you have an HCl right here. And then from here, right? The really funny thing that happens is that this will just kind of pop off on its own. Interesting, eh? This will pop off on its own, like an SN1. It'll make it a good leaving group. And then from here, I'll change the colors in a second. Right. Now, a very important thing happens here, right? Where these two, right? These little parts, these little two molecules right here, right? Will form an ion pair. Essentially, they'll just stick very close to each other. And that ion pair is tight enough that it basically helps retain stereochemistry. Yep. That's the reason why chlorination can be used to put Cl's, chlorines onto things that don't necessarily that to stop like any other types of stereochemistry from forming, right? So you can retain your stereochemistry. Very useful, right? The next thing that happens, right, is that this will stomp down. This will pop off, right? This little Cl will pop off. And then you'll end up having this, this right here, right? End up having a SO2 here, this right here. And from here, the Cl will finally be freed. The other Cl, then it will go and attack. Okay. Yep. Then your byproducts are going to have this little SO2 at the end here. Yep. Okay, cool. So if you guys have any other questions, please feel free to find me. And yeah, if you have, I encourage you that if you're confused at some point, watch the video over again. But other than that, please review your notes, right? And if you have any other questions, please let me know. I'll see you guys later. Thank you for watching.